So the outline for the talk roughly follows what Anthony would call the Polynesian model, where the generation is broken down into several steps. You start with some input text, and you would massage it into some phonemes or characters or other linguistic features. Then you fit it into some kind of acoustic model that spits out some variation of a spectrogram. Then you use a vocoder to turn it into actual wave samples, which correspond to air pressure as a function of time. So today we are in the tribe of Polynesians. There is actually a more comprehensive map for everything that, thanks to Phoebe that pointed to me this paper here. There are many models that TTS, many versions of TTS, and they all start with some text, and they some of them do some pre-processing, and then some of them use some intermediate features. In today's talk, we will be focusing on these 4 parts. So Tacotron 2, which takes phonemes and turns them into a spectrogram or MEL spectrogram or linear spectrogram, which are then converted into waveform using either, say, the Griffin-Lim algorithm or hi-fi GAN, which is a neurological model. And there are many other ways to do it, like the end-to-end stuff that reads, which Nick will be talking about tomorrow, just jumps directly from character to waveform. That's one way to do it. So maybe I would just first advertise a bit why do we take this approach of using this intermediate feature, MEL spectrogram in particular. So it was back in 2017, people just find that using MEL spectrogram as an intermediate engineered feature would help the model to be easier to train, because if you just ask the model to output directly the wave samples, it could be very discontinuous, and there are like thousands of samples per second. It could confuse the model a lot. So MEL spectrogram is just smoother in the time dimension. MEL spectrogram in particular, which means that you take the audio wave, do the Fourier transform, take the magnitude only, and then focus on the human speech frequency bands, which means zooming in into the lower frequencies. In particular, it's a good representation of human speech, somehow, because human speech have more emphasis on the lower frequencies. And later on in the talk, we also see that MEL spectrogram is used for duration modeling. You could see how every phoneme gets represented in some window of time. So you could just count how many MEL frames, which correspond to how long that sound should be. That allows you to do some manipulation later on. So to begin, we first focus on the acoustic model used in this pipeline. The acoustic model would roughly be of 2 different variations today. There is the Tacotron, which is the paper on the left, published in 2017, or the Tacotron 2, which is another paper published in 2018. So let's jump in. The Tacotron 1, they basically directly just predict the linear spectrogram from the characters. The innovation there is that it's now using attention-based modeling, and it's also autoregressive. Very roughly speaking, the Tacotron 1 can be split into 2 parts. One part is the encoder part, which takes the character and then make them into some kind of hidden vector, which has the same length as the number of characters. And the second part is a decoder part, which splits out linear spectrograms. And the whole process is autoregressive, meaning that every linear spectrogram produced has to be produced one by one. So the new linear spectrogram refers to all the old linear spectrogram as well as all the character embeddings computed by the encoder. Something very interesting parameter that you could tweak in this Tacotron 1 is so-called the reduction factor R, which control how many MEL frames you generate per decoder step. So sometimes you don't generate it frame by frame, but maybe sometimes you generate 2 frames at a time or 3 frames at a time. And people find that adjusting this reduction factor has a huge impact on how stable the model is, and as well as the quality of the output. And I tried really hard to find out why it's called the Tacotron, but it turns out it's just because these authors really like tacos. Let's check out some samples for Tacotron 1. So it sounds like this.
Generative adversarial network or variational autoencoder. Basilar membrane and otolaryngology are not autocorrelations.
It's resilient to spelling errors.
This is really awesome.
And punctuations as well.
This is your personal assistant, Google Home. This is your personal assistant, Google Home.
As well as capitalization if you have the right data set.
The buses aren't the problem, they actually provide a solution. The buses aren't the problem, they actually provide a solution.
Well, those samples, in my opinion, sounds a bit cherry-picked, but anyway, that's what everybody does. So these are some samples. 1 year after, they switched to Tacotron 2 as the state-of-the-art TTS. The differences is that in place of the Griffin-Lim algorithm, which is not using any neural models, it uses a WaveNet instead. So it's just a much more fancier way to generate the audio frames from the MEL spectrogram. And it has a higher mean opinion score, which is approaching the human human ground truth labels. And it's only 26 million parameters. So very roughly, it still has an encoder part. Well, it looks a bit simpler than before. And a decoder part, which makes use of a so-called location-sensitive attention. So every time you are trying to make a new MEL spectrogram, you would compute some attention score that tells you which encoder frame you should be attending to. So this is an example for the attention score. The y-axis is the number of phonemes. The x-axis is the time frame. So for each time frame, you look at which phoneme you should be attending to before you generate that MEL spectrogram. The decoder has a prenet. Very interestingly, it has a dropout of 0.5. That means 50% of whatever is going into this prenet is actually thrown away in the next step of the decoding process. You might be wondering, why do we throw away that much stuff? Would it not make the output very noisy? Well, there is a little bit of philosophical discussion there that I'm going to show you in the next slide. But very roughly, the model just has an encoder and decoder, and then it has some final postnet to make some polishing on the output MEL spectrogram. And the final output would be the MEL spectrogram on one hand, and also the stop token, which is simply a 0 to 1. Well, actually, it's a sigmoid. It's an input to a sigmoid function, which tells you whether it's time to stop or not. So let's get back to this dropout 0.5. So in TTS, why do we inject noise in general? Why is noise useful? That's because TTS in general is a one-to-many problem. Given the same text, say hello, there are many ways to pronounce it, like hello, hello, or hello. So you don't want your model to just output one point in the output space, in this case, MEL spectrogram. If you're given one point in the input, in this case, the text hello. What you really want the model to do is to give you an output distribution. So given an input X, you want it to give you a blob, a big ball in the output space that tells you how probable each output should be. But in order to make it output such a blurry object, during training, you also want the model to know, okay, this is like adjustable. You don't need to follow exactly from the input. So we inject some noise into the training process. In the case of Tacotron, you do it by tuning that dropout to be 0.5. But say in width, we actually directly inject some Gaussian noise into our input. Well, Nick will mention that tomorrow. but that's just a general feature of any generative model. You want it to output a distribution, not just a point, which might also, you could think of it as a difference between generative model and regression. Anyway, so that's just some philosophical fussing. Well, the Tacotron 2 loss has 3 parts. LPRE, which just takes whatever decoder output here, and then basically measure the distance between that decoder output and your ground truth MEL spectrogram. And there is another LPOS, which takes, after the polishing layers, you take the output here and then compare it with the ground truth MEL spectrogram. And then the third is LSTOP, which is just making sure these stop tokens are produced in a reasonable way, because every data point you have, you know when it's going to stop. So you want the stop token to predict precisely this is where we should stop. Otherwise, it would go on forever and make creepy noises. So here are some samples.
Generative adversarial network or variational autoencoder. Basilar membrane and otolaryngology are not autocorrelations.
So I guess compared with Tacotron 1, you might feel that the voices may be smoother and more natural. So that's Tacotron 2. Well, there is some shortcoming for this kind of attention model, because this attention alignment that I showed you before has to be learned by the model itself. There are good days where the model just...
My name is Grace. Thank you for calling. My name is Grace. Thank you for calling.
Good days when the model just outputs some nice monotonic attention alignment where the audio would sound good. But sometimes the model would just derail at some point, just losing attention. So it might skip some phonemes, for example, in this case.
Thank you for calling Bright Smile Dill.
Maybe here the dental is not very well pronounced, just skipping some letters. But this might be a good way of debugging your model, because more often than not, if you see a good sharp monotonic attention, you will have good audio. And if you don't, mostly bad audio. And there are many tricks people use to improve this alignment so that the model performs better. A lot of work went down that avenue, but in hindsight, I don't think that's the right way to go. Well, I'll mention about this towards the end. Anyway, so that's the acoustic model part. Any question so far at this point? Cool. Then we could move on to the vocoder, which takes your spectrogram and turn it into actual audio. So for today, I'm just going to mention 2 main algorithms, Griffin-Lim and Hi-Fi GAN. So Griffin-Lim algorithm is quite simple. So you're given a MEL spectrogram, which is basically the Fourier transform of your audio without the phases. You only take the magnitude. So what you want to do is to fill back the phases into the magnitudes. You could argue that actually you are losing some information, but it turns out if you just start with some random phases, you just generate randomly, and then repeatedly do inverse Fourier transform and Fourier transform repeatedly, somehow you recover a nice phase. So I think it's provable that this process actually converges, and it actually doesn't sound that bad. The nice place is that it has no parameters at all. You could run it in a very simple CPU machine, just that the quality is not very good. To demonstrate how simple this is to do, we have a demo here. So I have here a Jupyter Notebook where I just take some input audio that sounds like this.
Welcome to Gridspace IAP Lecture 2025. This is a demo for Griffin-Lim algorithm.
This is one of the generated audio for Grace. And we do a Fourier transform, make it into a spectrogram, separate the amplitude part and the angle part. What I'm showing here is a linear spectrogram. So I just show you the amplitudes in a log scale, basically. And then if you keep both the angles, which are phases, and the amplitudes, you could show that this preserve the audio, so you could do a inverse Fourier transform and give you back exactly the same audio as before. So if you do inverse Fourier transform, you get the same audio.
Welcome to Gridspace, IAP Lecture 2025. This is a demo for Griffin Lim algorithm.
And there is no loss of information because the diff is basically 0. So let's move on to the Griffin Lim algorithm. We begin with a randomized angle, so there has no, it has nothing related to the original ground truth angle. This is just completely random. And then you could do one iteration of Griffin Lim algorithm, where you do inverse Fourier transform and then a Fourier transform. And that's done. Initially, it sounds really robotic. But,
Welcome to Gridspace, IAP Lecture 2025. This is a demo for Griffin Lim algorithm.
But with more iteration, it would improve a bit. Like, give it 2 more iterations.
Welcome to Gridspace, IAP Lecture 2025. This is a demo for Griffin Lim algorithm.
And then you could just let it run forever. In this case, let me run it for 100 times.
Welcome to Gridspace, IAP Lecture 2025. This is a demo for Griffin Lim algorithm.
So that's that. You could run it on a CPU. Well, I have not presented to you a proof of why it converges, but if you take all the, you could compare the C, which in this case is the complex number, and then you just plot the differences between subsequent steps. You could see that the differences would converge to 0. So it gives you some confidence that this process actually end up being stable. But anyway, so you could do that just without any modeling, just Fourier transform, inverse Fourier transform, keep doing that. But there are better ways to do that. One of the ways that eventually stuck around is so-called hi-fi GAN, which Anthony also briefly mentioned yesterday. It consists of 2 parts. One is a generator part, one is a discriminator part. That's why it's called a GAN, generative adversarial network. These 2 networks fight against each other. So the goal for the discriminator is so that when it's given ground truth real audio wave samples, it would label it as 1. When it's given generated samples, it will label it as 0, meaning that it knows the difference between real and fake. Whereas the goal for the generator is just to confuse the discriminator. It tries to make audio such that the discriminator would think it is real. And that's a simple loss function. And then you let them train. These are some architectural details for the generator. It basically consists of some scaling up convolution. Your goal is to convert MEL spectrogram into wave samples. So you would be increasing in the time dimension, but reducing in the MEL spec dimension. In this case, the model is relatively lightweight. It has only 14 million parameters, and it's not autoregressive. You could do it in one go. So you don't have to worry about computation latency. Actually, the most parameters goes into the discriminators. There are 2 variations. There is a multi-period discriminator, multi-scale discriminator, which both works essentially by extracting different features from your wave samples. Yeah, so output label is just real or fake, 0 or 1. So for hi-fi GAN to train stably, it's not sufficient to have those 2 loss terms for the discriminator and generator to fight against each other. There are also additional helper loss terms, like MEL spectrogram loss, which just helps the generator to generate something that should have a short R1 distance with the ground truth audio. So this is a MEL spectrogram loss. The generator should output waveform, which when you convert it into mouse spectrogram, it has a short L1 distance with the ground truth. And then feature matching loss, well, the discriminator extracted some features out of the waveforms. So generator should produce some kind of waveform so that those extracted features, according to the discriminator, should be close in some sense. So final loss would be a combination of the adversarial loss, which were presented in the first slide, the mouse spectrogram feature loss here, and the feature matching loss here. So with some patience, you would get it to work. In practice, most of the magnitude of the loss comes from the mouse spectrogram loss. So here are some audio samples of hi-fi gain generated wave samples.
Welcome to Gridspace IAP Lectures 2025. Okay, so I have your first name spelled as N-N-I-S-S-I-P-P-I. Is that correct? I protected Pecca pick up peppers. She sells shells by the seashore. Leather, never weather better.
So this was the old grades that we used until last year. So just a brief overview of what we have so far. We talked about the acoustic model, in this case, Tacotron 2, and a vocoder, in this case, hi-fi again. Any questions so far? Yep.
So why can't you just backpropagate through the inverse Fourier transform to try to compare the audio signals directly?
So the question is, why can I backpropagate through the inverse Fourier transform? You mean when you train the vocoder, or?
I mean, just forget, like, instead of hi-fi gain or Griffin limb or anything, just like instead of having a loss from the mel, just do the inverse Fourier transform and then have the loss come from the wave form directly.
Oh, you mean the feature loss between generated and non-gen, and then the ground truth should just be in the waveforms directly?
Yeah.
Well, I guess that intuitively makes sense. Ultimately, you want the generator to give you same thing as the ground truth. It might be too difficult because multiple waveforms could correspond to the same mouse spectrogram. You could have a very different phase that could still correspond to the same mouse spectrogram, but it just corresponds to different audio waveforms. So if you do that, then you are not allowing the model to be a little bit creative about the phase. I think you might want to preserve the model to be generative on the phase. So if you do that, it would be too strict. The model have to produce this exact audio. Maybe we don't want that. We want it to be a little bit creative. It's okay if you change the phase a little bit. As long as it gives you the same mouse spectrogram, I'm happy. I think that's what you want the model to do. Right, thanks for the question. So that was an overview of the models themselves. I'm just going to tell you what happens during training. So in training, we go kidnap a human expert, and then we extract some data out of the human expert. In this case, the data consists of a pair of audio and text. Well, audio has both the phase information and the mouse spectrogram information. We put the mouse spectrogram and the text into the Tacotron 2 for training. And we put the audio wave and the mouse spectrogram into the hi-fi gain for training. So that's how training was done. During inference, a user would have some text as an input to the model. So this text would go into the Tacotron 2 that we trained so that when they see the text, it know what mouse spectrogram is supposed to look like. This mouse spectrogram would then go through a hi-fi gain, the vocoder, to output an audio wave. And once we have the wave ready, we could pass it back to the user so that it would make him happy. So throughout this process, there are things we could do, like this intermediate representation of the mouse spectrogram. there are something we could do with it. In the future end-to-end models, this is more difficult. It's still doable, but here we could do something. And we do something to the MEL spectrogram because, well, one thing, we are just engineers and we don't know anything other to do than tinkering with stuff. And another thing is that it's actually useful for some clients who want the grades to speak slower because they are supposed to be talking to elderly people who wants people to slow down a bit. So, so one particular avenue for modifying MEL spectrogram is just stretching the MEL spectrogram. So you could just take the intermediate output for the Tacotron tool and just linearly stretch some part of the MEL spectrogram. So without any stretching, it would sound like this.
Welcome to Gridspace IAP Lectures 2025.
But if you try to take whatever spectrogram you generated for welcome and then just stretch it 10 times in the time dimension, the vocoder will still accept it and produce reasonable outputs like this.
Welcome to Gridspace IAP Lectures 2025.
So that's one way to use it. Oh, by the way, the vocoder is actually, yeah. The question is that assumes you have phonemes that you could scratch. And the second part is a stop consonant cannot be done. Yeah, so in our case, the phonemes are all pronouns with a voice. There are no hidden stop tokens or something like that. But you raise a valid concern. Stop token in our case would be oh, I see. Right. So for some consonants like the, you cannot really stretch them out. You raise a valid point. What we are doing here is actually a very rough scratching. So every phoneme will just give it a timestamp, which is very roughly identified using the attention alignment. So it's not precise, but that's a valid concern. Thanks for the question. So at this point, maybe you would be wondering what is going to happen next. What happens next in the history of TTS is that we just get rid of things that are engineered by humans. So we no longer use engineered linguistic features. We no longer use this MEL spectrogram intermediately. And instead, the trend is towards a more end-to-end model where you just give the model some text and you expect it to output directly the audio wave signals. And it just happens to what the history is telling us to do. You just scale up your model, let it figure out what feature it wants to use. And Nick would mention about this tomorrow. So finally, I have also take a figure from the paper that, well, Phoebe pointed to me that shows some history of TTS models. So back in 2016, it started with some WaveNet, and then it branched out. Tacotron and Tacotron 2 are here, which are just acoustic models. And Hi-Fi GAN is here, which is a vocoder model. But eventually, people move towards more end-to-end model, like Grids, which Nick will be telling you about tomorrow.
Model.
Yeah.
In this, you described it as being used as a vocoder to go from MEL spectrogram to audio.
Well, it's actually can be both. All right, sorry. So yesterday we mentioned WaveNet as a model, more end-to-end model. But in today's talk, it seems that I'm using WaveNet as just a vocoder to get the waveform from the MEL spectrogram. So the answer is that WaveNet is more flexible in its input. It could either take in engineered linguistic features. Well, it might be best if I go back to an earlier slide. So like in this figure, it shows WaveNet takes linguistic features and output waveforms. So these linguistic features can be very, very engineered. It contains some prosody information, word segmentation, and text normalization. it just turns out that WaveNet, the input, you could also take the input as a linear spectrogram. You could just use linear spectrogram or MEL spectrogram. Well, in the case of Tacotron 2, it used MEL spectrogram as the input for WaveNet. It's accommodating to different types of inputs.